Hello everyone and welcome to this next lecture on Python Power Electronics, and this lecture will be a continuation of the previous lecture where I talked about pulse width modulation, and in this case I'm going to talk about how we can use filters to filter the output of this inverter. So to begin with, I'll just go over and let's get started with my simulator. So first, as always, let's activate the virtual environment. So this is the virtual environment. Now that this is done, I shall go into and I will launch the circuit simulator. So the simulator is running. We can just go to the web browser and click on 127. So if you're wondering what this link is right here. You can just copy this link and paste it in your web browser. Same thing. Okay. So simulation library. This was the previous one, which is just to show you how to simulate a circuit. Then I talked about square wave modulation, or rather rectangular wave modulation, and then I talked about pulse width modulation. Now, in both of these cases, let's go over to those things. So this is virtual environment. This is the single UPS simulation. These are simulation files. And in square wave, we got this as our Fourier spectrum. So there's a fundamental and there's low frequency harmonics. And the output and the fundamental look like this. The output is this rectangular waveform, which is the blue line, and the orange line is the fundamental component. Now, though a fundamental component exists, the real voltage which is applied across the output is this one. Alright, so you are applying a square wave, a rectangular wave. I should stop saying square wave, it's a rectangular wave. Now, a rectangular wave is not acceptable in many cases. Alright, particularly in the case of sensitive loads which need a sinusoidal waveform. Alright, and similarly, even if we go to pulse width modulation, what we get is this. So the blue line is the actual voltage, which is a high frequency switched voltage, and the yellow line is the fundamental component. So as before, even though there is a fundamental component, the voltage which is applied across the output is a high frequency switched voltage, which is quite often not acceptable. So in both of these cases, we need to apply a filter, because what we want is this fundamental. We need to get rid of everything else. Even in the previous case, what we want is the fundamental. We have to get rid of everything else. So for that, we go to this other folder, and that is called filtered output. Okay, and filtered output contains again these two simulations. Only difference now is I'm going to talk about how there's also a filter. So let's start with square wave. So the first thing is the inverter leg. The inverter leg is the same as before. I'll just open that circuit. So, okay. So, as usual, the circuit is the same. A single leg of an inverter with an upper switch and a lower switch, and the midpoint except midpoint is accessible, and you have two DC voltages with the midpoint accessible. We are measuring the voltage across the midpoint. Now, in the previous case, we were only measuring the voltage. Now, we are going a little ahead. You see here, I have a jump label. So I am actually extending this schematic. So let's go back to the circuit here. If you see here, there is another file called inverter output, right? And this is a circuit file. You know a circuit file when you see an output.csv, or you see a .csv file and you see an underscore params.csv file. This is an indication that it is a circuit file. So open this circuit file. And what we have here is a filter and the same resistor and voltage output. So we are measuring the voltage at two places. We are measuring the voltage directly at the output of this, at the switched output voltage of the inverter or the inverter leg, and we are measuring the output that is finally available after all this. Now what is here? Alright, the jump label extends. We have an inductor, we have an ammeter for measuring the current, we have a resistor. The resistor is basically the parasitic resistor of this inductor. We have a capacitor. A resistor is again the parasitic resistance of this capacitor. Remember, whenever you have any component, you must have a resistor in the branch. A branch with a zero resistance is illegal. Okay, so these are all negligible parasitic resistances, and there is the load resistor, and there is the output. We are measuring the voltage output. So what is this inductor capacitor? This inductor capacitor is the filter at the output of the inverter. Okay, an inductor itself forms a filter, a capacitor itself forms a filter, and their combination forms a second order filter. Okay, a second order filter means it has double the filtering capability of a normal filter. Okay, now I'm not going to go into mathematics. I will try to avoid it as much as possible, but if you are interested, you are very welcome to look into the inductor capacitor filter concept. Okay, an inductor capacitor filter has a lot of publications, has a lot of frequency analysis, and it will show you how this filter has a resonant frequency which is the square root of these two. Alright, it is rather the reciprocal of the square root of these two. So if this is our inductor, then 1 by square root LC, this is the resonant frequency. Alright, now this is a very important number, for the reason is simple. By changing inductor and changing capacitor, you can change the resonant frequency, and therefore you can change the frequency at which you begin to attenuate the output. Alright, so I'm just going to remove this. Let's just save it anyway. No, I don't want to save it. Now that this is done, let's now just run this simulation, and of course we can always open the output, square wave. Here there is no frequency analysis, right? Fourier analysis rather, because I've already showed you that. There's no need to show you again. What I'm going to do this time is the same old rectangular wave modulation, that is, take a modulation signal which is a cosinusoid, compare it with 0, and switch on the upper switch in the positive half cycle, switch on the lower switch in the negative half cycle. That's it. Now that this is done, let's just start a simulation. So let me call this single UPS. Let's call this filtered output with square wave modulation. Alright, and I'll just copy paste it here. You're always welcome to add a detailed description. I won't do that. Now to get the path of this directory, I right click, go to the folder, copy paste, and let's paste it here. So I'll save the simulation parameters. So everything has been saved, so that means no error. Let's go back, add circuit file. So here remember there are two circuit files, so let's add both of them. So the first one, always remember to go into the right directory. Oh, no, this was not it. Inverter leg. And let's add the other one, that is inverter output. So inverter output has the filter and also the output. Let's call this filter. Save circuit. So these two are done. As always, now that you added the circuit files, you must click on process circuit schematics. So something is done. It says the circuits do not have any detectable errors. You can continue to main page. So let's continue to main page. Now the time has come to edit the component parameters. So let's go to inverter leg. These are the parameters. As I said before, if you want, you can change each and every one of them individually. Here I'll just upload the parameter file. So I will upload inverter leg underscore params, upload this file, and you see the parameters have updated. Go back to the circuit list and let's do the same thing for the next circuit, that is inverter output. As before, we shall upload the params.csv file. So check again, yes, it has updated. Now let's go here and look a little about the values of the filter. So there are two of them. There is the inductor. Here I have chosen a 1 millihenry inductor, and there is a capacitor. The capacitor is 0.0001, which means it is 100 microfarad. Okay, it's a 100 microfarad capacitor and a 1 millihenry inductor. Now let's go back and add the control file. The control file is just one, which is square wave.py. Let's call this square wave modulation, and let's configure this file. As before, it's empty because we just created it. All we have to do is upload the descriptor file. So it has been uploaded. You see all the values have come. And let's go back to the main page. So everything is set. We can now run the simulation. So let me click on the run button. So as always, go to the terminal and check if there is any other cryptic error. No, there isn't. It is indeed running. So of course there is only one real plot we want to check. Just to check if the circuit is working, it's always advisable to check if the circuit is working after clicking the run button. So output voltage. So let's click on V out. So remember, there are two V outs. There is V out, which is the output of this inverter leg, which is going to be a switched waveform, and there is voltmeter inbound, V inbound. This is the filtered output. Okay, so let's call this VO, save it, and let's take V inverter out and let's call this V filter. Let's click done and let's plot this. So something's happened. Let's close on this and let's open this file. So you see here, this is the difference. Now the blue line is the output voltage, which is our rectangular waveform. The orange line is the output at the filtered output. Now few comments. This orange line isn't really doing much. Alright, all we've done is to put some oscillations around it. Now you might wonder where these oscillations are coming from. Now simple thing is this: when you have an inductor and a capacitor, almost always you form an oscillator. Alright, an inductor capacitor typically forms an oscillator. So if your frequency is such, and if you do an analysis of this, if you were to do, and I would strongly encourage you to, you will find this frequency of oscillation will be the resonant frequency which I told you before. Okay, now this is your homework. I won't talk about it. Let's go on. But what's important here is this is completely useless. Alright, if we could not apply the blue voltage, which is the rectangular waveform, we cannot also apply this orange waveform. This orange waveform is almost useless. So what do? what this shows is that we have so many harmonics, or the harmonic content, the low frequency harmonic content is so significant that we are not able to make hardly any change to the harmonic spectrum. That's why we have almost everything, which means if you see, it's almost what we want is a sinusoid. What we end up getting is just a square wave with some oscillations on it. So what this means is, if we want a sinusoid, we have to decrease our resonant frequency. And when you say decrease your resonant frequency, we need to increase our filter component, because remember, it is 1 by root of LC, and if it is 1 by square root of LC, it means by increasing inductor or increasing capacitor, I will now be able to increase the filtering output. So let's do that. So I think there's not much to be seen, so let's just stop this. Let's go back and let's edit the circuit parameters. We need the inverter output can be the same, the inverter leg rather, the inverter leg can be the same. It's the inverter output that we need to change, because that's where the filter is. So we have the inductor, we have the capacitor, or rather the inductor and the capacitor is ahead here. So let's start with the capacitor. Let's edit this. Let's make it 10 times larger. What difference does it make? It's just a simulation, right? It's not hardware. You're not actually connecting a physical capacitor. If you were connecting a physical capacitor, then you would have to worry, because this is a 1 millifarad capacitor. That's pretty huge. So let's go back. And let's run this again. Now, before I go ahead, I need to tell you that you do not have to be at this page, all right, because it's running. You can always go back. That's not a problem. You can go back, you can browse, you can do anything you want, you can come back. The reason is, what I'm using is, you see it's still running, right? By moving away from this page, you do not stop the simulation. What I'm using is a concept called multi-threaded. So when I run the simulation, I am starting a new thread, all right? So you can still continue navigating your circuit simulator, no problem. So now that we have this, let's just plot this. Okay, something has happened. Let's click on this. So you see the oscillations have actually increased, but really speaking, what's happening, you see, is it is beginning to resemble a sinusoid. All right, that's what it is doing. It's resembling a sinusoid. Now, what will you do here? We've increased the capacitor by a factor of 10. Let's increase now the inductor also by a factor of 10, because it's quite obvious that this is not enough. All right, this is not enough. Now I'm going to show you that this entire concept is not enough, but I'm just going through this process to tell you how pulse width modulation is better. So now that we've increased capacitor by 10, let's increase inductor also by a factor of 10. All right, a 10 millihenry inductor. You want to add a 10 millihenry inductor to any power converter, good luck. All right, this is a huge inductor, huge. So again, let's go back, view output, and let's click on run. So this circuit will take some time to run, and I'm going to just pause the simulation and let it run. We could just plot it just in case, just to see if it's okay. So you see it's beginning to slowly become more of a sinusoid. All right, there's a rectangular waveform. Before it would just go into oscillations. Now you see it is resembling a sinusoid. Now, simplest thing to do, I'll just come back here, plot it again. Usually it's best just to let the simulation run for a while and plot later, usually. All right, in this case, I don't really want to progress that much with the simulation, because like I said, this simulation is not what I want to show you. I want to show you the pulse width modulation. This is just to show you the implication of using a square wave modulation and what is the major challenge in filtering out a square wave. So you see here, now we are now achieving a sinusoidal waveform at the output. Remember, the blue line is the output voltage exactly at the inverter. The filtered, that is the orange line, is the filtered output voltage which the output, the load, is beginning to see. So let's just run it again. We should have got one more waveform. And yes, we do. You see what's happening here? You see here, this orange line is now a sinusoid. Now, a couple of observations is: one, the sinusoid has a huge phase shift. And the reason for this phase shift is simple. You have a huge inductor. That inductor is going to have a huge voltage drop across it, which phase shifts this entire output voltage. That's number one. Number two, we actually have a huge voltage boost at this output, right? I thought it would, you thought like you applying 100 volts, you thought you would get 100 volts, right? But the problem is this: when you have an inductor capacitor filter, like I said, an inductor capacitor also behaves like an oscillator. An oscillator sometimes tends to boost the output voltage. So the inductor stores charge and tends to discharge this, which again ends up charging the capacitor, right? This is how it is. An inductor is an energy storage element. So it stores charge and it discharges again. So it stores it, releases it. So when this energy gets released, it gets released into the output capacitor, which is why the voltage of the output capacitor is greater than the voltage of the inverter output. This is nothing much. If you go back to your basic power system concept, you would have learned this. A lightly loaded power transmission line can have a voltage at the receiving end which is higher than that at the sending end. Why? Because all the charging capacitors throughout the line are now adding their voltage, and the result is the voltage at the receiving end is greater than that at the sending end. Okay? So, as before, like I said, the concept here is to show you that if you wanted to produce a sinusoidal voltage at the output, okay, supposing you had a load which says you have to apply a sinusoid only, you cannot apply a rectangular waveform or anything else, it must be smooth sinusoid. This is what needs to be done if you have a square wave. Alright, you need a huge filter. Now, if you have any practical experience in power electronics, that is, if you've been building power electronic circuits, anyone who builds a power electronic circuit, if you tell them that you're using a 10 millihenry inductor, they will scream. Alright, this is a totally impractical inductor. This is huge, extremely bulky, and you cannot design any power supply with something like this. Same thing with a capacitor. It's 1 millifarad capacitor is a very large capacitor. Usually a capacitor sizing is not that much of a constraint as an inductor sizing. Any power supply designer is going to try to minimize the size of the inductor as much as possible, and this is way too large. Alright, but this is what is needed. If you want a smooth sinusoidal voltage, this is what you have to do. It's as simple as that. So let's just run this plotted one last time just for good measure, since we are here. Nothing much. I mean, we just continue to see more of the sinusoidal waveforms, more cycles, and that's what you see, more cycles with the sinusoidal waveform, and it has stabilized. So even though you have a sinusoidal waveform, such a circuit is quite often impractical. And long back, if you were to notice, square wave modulators were either one, very bulky, or two, they would end up actually applying a square wave at the output. So you would actually, the output would be a rectangular waveform, would not be a square waveform, it would be a rectangular waveform. So for these reasons, this modulation technique is now completely outdated. I don't think anyone uses this. It's always pulse width modulation, or there are other advanced forms of modulation. There is things like space vector modulation and things like that. Those are different. I will talk about that maybe in a future lecture. But when you use square wave modulation, this is the burden that you must bear. That is, very large filter elements in order to achieve a sinusoidal voltage waveform. So this is going to be the justification for using pulse width modulation, which I am going to do in the next lecture, which I hope will be tomorrow. So for now, I am going to end this lecture. As before, I try to keep this lectures as short as possible. I am going to end this lecture, and if you have any doubts or any questions, feel free to message me on Facebook or email me. Otherwise, just wait for the next lecture to come out. So thank you so much for watching, and see you soon. Goodbye for now.